All right, let's work through the first sample problem where we're solving the titration of a strong acid with a strong base. Okay, so here's what we know. We know 20 milliliters of 0.5 molar HCl is to be titrated with 0.25 molar NaOH. So in zone 1, we want to find what is the pH before any titrant is added from the burette. Okay, so before we add anything, the pH just depends upon the concentration of the acid or the base. So we use the molarity of the acid or the base to determine the pH. If we know the concentration of the acid, it's easy. It's just the negative log of the hydrogen ion concentration. Of course, if we know the concentration of the base, we find the POH, the minus log of that concentration, and subtract it from 14. Okay, and just double check to make sure you don't have a polyprotic or polyhydroxy acid or base, so that you're accounting for all of the hydrogen ion or hydroxide ion concentration. So in our example, we have 0.5 molar acid that's being titrated. So that's our hydrogen ion concentration. So the minus log of the hydrogen ion concentration gives us our pH, 0.3. Okay, that's our starting pH. That was the important part of zone 1. Now, we can also calculate the volume to the equivalence point here, just so that we can keep track of what segment of the titration we're in as we add milliliters of base. So let's calculate the volume of the titrant needed to reach the equivalence point at the beginning, so that all the way throughout the problem we know what segment we're in. So again, these are both HCl, NaOH. It's 1-to-1 stoichiometry here. So MAVA equals MBVB. So the volume of the base is the concentration of the acid times the volume of the acid over the concentration of the base. And so our equivalence point is going to happen after 40 milliliters of NaOH have been added. In zone 2, that's when some titrant is added from the burette before the equivalence point. Okay, so remember the equivalence point occurs after the addition of 40 milliliters of base. So we just should choose anything before that 40 milliliters. So here's an example. If I start again with 20 milliliters of 0.5 molar HCl, titrated with 0.25 molar NaOH, what is the pH after 10 milliliters of base is added? So I know I'm before the equivalence point because I'm before the addition of that 40 milliliters of base. Okay, so we have to write down first our neutralization reaction. So what's happening? HCl plus NaOH is making NaCl in water. And we have before the neutralization, during the neutralization, and after. So we've seen this before, but again, all of these amounts are in moles. So let's just make sure we know where this comes from. So to get that 0.01 moles, I have to use my starting amounts of HCl. So 0.5 molar, that's moles per liter, times 0.02 liters gives me 0.01 moles. Okay, that's where that 0.01 moles of HCl comes from. Same thing with the NaOH. I have 0.25 molar, and I've added 10 milliliters, so 0.01 liters. That's where I get this 0.0025. Okay, 0.01 times 0.25 is 0.0025. moles. Okay? Now, we're not at the equivalence point yet, right? So we're going to use up all of the base that's been added. So I use up all of that base, use up some of my acid, and here's my amount of moles of acid that's left. Now, in order to find the pH, I need the concentration of the acid. Well, concentration is moles per liter. So I take this moles, put it in here, moles per. Now, our volume has increased, right, by 10 milliliters. So 10 plus 20 is 30 milliliters, or 0.030 liters. So I have now an H plus concentration of 0.25. The negative log of that is 0.6. So we started with a pH of 0.3. We add 10 milliliters of base, the pH increases to 0.6. Okay, so what about finding the pH at the equivalence point? So our same initial amounts of materials, 20 milliliters of 0.5 molar HCl, and we're titrating with 0.25 molar NaOH. What is the pH at the equivalence point? So what do we know at the equivalence point, or how do we know that we've reached the equivalence point? Well, that means that the moles of acid equal the moles of base. Okay? If the moles of acid equal the moles of base, that means there's no excess H plus or OH minus, because they're equal. So we have to look to the salt that is formed to see if it will affect the pH. Okay? Since in this case we're talking about the titration of a strong acid and a strong base, the salt that is formed will not undergo hydrolysis and therefore will not change the pH. In cases such as these, when a strong acid and strong base are titrated, the pure water will have a pH of 7. Okay, so what about beyond the equivalence point when excess titrant has been added? So we start again with our same initial amounts and concentrations, and we're asked what is the pH after 45 milliliters of the base has been added. So we start with our neutralization reaction. We have the same initial amount of HCl, 0.01 moles, which remember is 0.5 molar times 0.020 liters. Okay, now moles of NaOH is 0.25 molar times the volume, 0.045 liters. Okay, we do that, we get 0.01125 moles. So we see here we have more NaOH than we do HCl. So we use up all the HCl because we're beyond the equivalence point, and we're left with an excess of NaOH. Okay, and we can find the concentration of that, 0.00125 moles in 65 milliliters, right? So 45 plus 20 is 65 milliliters, or 0.065 liters, and we get a concentration of 0.0192 molar. This is the concentration of hydroxide. So we take the negative log of that gives us a pOH of 1.72. Subtract that from 14 and we get the pH of 12.28. So right after that equivalence point, we added 5 additional milliliters, right? The equivalence point was at 40. We had 5 additional milliliters, and the pH jumps rapidly from 7 to 12.28. One more time, we'll look at this on a pH curve. So if I start with acid in the flask and I titrate it with base, again, I start with a really low pH down here. This is my zone 1, my starting pH. Then I have, after a small amount of base, the pH only increases slightly. At the equivalence point, because we're talking about a strong acid and a strong base, that has to happen at a pH of 7. And then, of course, a very small addition of any more base will cause this rapid increase in pH until it levels off. If instead of starting with acid, I had started with base, then the curve would look something like what you see in red here, where you start with a very high basic pH in zone 1. After a small amount of volume, you have a very small or slight change in the pH after you've added some acid. The equivalence point still happens at 7 because we're still titrating a strong acid and a strong base together. And then, of course, after a very small addition of acid in excess beyond the equivalence point, we get this rapid decrease in pH until it levels off.